beloved colleague, our beloved colleague and friend, Professor Gauthier from Université de Montréal, emeritus professor or extinguished professor, who's going to talk about limits of harmonic and holomorphic functions along segments ending at the boundary. Cher Paul, s'il vous plaît.
Merci beaucoup, Javad. Thank you for the invitation. It's a great honor for me to be allowed to participate in this session. This is the way I usually show a screen, but let me try and show the traditional way. Yes, I think that's the more traditional way of showing it.
That's good.
Full screen. Okay. Anything I knew I might say here is joint work with Mohamed Shirazi from McGill University, this particular page maybe you shouldn't look at too seriously because I've used the word sampling before, and I would just for myself I wanted to try and hook up the word with what I want to talk about. I want to talk about approximation, and so. For me, approximation is related to extension. If you have a subset of S in X, and you have a function defined on S to some space Y, well, extension means find function capital F on the bigger space X to the same space Y, which equals little f, where little f is defined, namely on S. Now, approximation means that instead of being equal is close to little f. And so, but in analysis, extensions are usually unique. And so usually they don't exist. Here's a definition of an analytic agnostic, a person who believes there's at most one God. So because extensions are difficult to do in analysis, I view approximation as an analyst's substitute extension. And I consider it to be a good substitute because by Heisenberg's uncertainty principle, if the epsilon is small enough, say smaller than the diameter of an electron, then no instrument, no even future instrument, will ever be able to detect between epsilon and 0, and therefore will not be able to detect the difference between the approximation f and the original function f. Complex approximation. On compact sets is well known, but on closed sets, well, it's also well developed, but not so well known. The following theorem of Carleman, proved in 1927, is a very beautiful theorem that should be better known. It says that for an arbitrary continuous function phi and an arbitrary positive continuous function epsilon on the real line, there exists an entire function f, which approximates phi within epsilon at every point of the real line. So since epsilon is an arbitrary positive continuous function, it's interesting to think of epsilon as going to 0 very fast as you go to infinity. It's allowed, you can do that. And let me give an example of how powerful approximation on closed is. There are many applications, but the one I prefer is solving the Dirichlet problem for the upper half plane. This was done by Neb and Lin in 1925, and the problem is, given phi, a continuous on the real line, to find, does there exist a continuous function closed upper half plane, harmonic on the open upper half plane, which agrees with the original data on the real line? Well, Neb and Lin proved that the answer is yes, but a proof using this approximation theory was given only in 1955 by Kaplan, and it's short. Here it is. Kadleman's theorem tells us that there does exist an entire function which approximates the data on the real line to within, say, epsilon equals. And then you just write the solution. The solution U is the Poisson integral of the function phi minus f plus the entire function f. Well, it's easy to check that this is a solution because the Poisson integral has boundary values phi minus f. F is an entire function. It's holomorphic on the real line, so it has values f. And so the sum of the boundary values is just phi. So U has the right boundary values. Okay. Now, why didn't we just write the Poisson integral of the original function, phi? Phi is an arbitrary continuous function, and so it may not be integrable with respect to the Poisson kernel. Whereas phi minus f is bounded, and all bounded continuous functions are integrable with respect to the Poisson kernel. So I really like this proof. It's quite slick. Potential theory, there are negligible sets, sets that are small. A set is E is said to be polar if there is a subharmonic function in a neighborhood of this set E, such that E is contained in the set where the function takes the value of minus. Remember, subharmonic functions take values can take the value minus infinity. They can't take the value plus infinity, but they're allowed to take the value minus infinity. For example, the log function takes the value minus infinity at 0. A compact set is polar. This is not a definition. I just gave the definition. This is a theorem. A compact set is polar if and only it is of zero capacity. And capacity, of course, is very important in potential theory and in physics. Polar sets are undetectable by Brownian motion. I think that's one of the nicest intuitive ideas of what a polar set is. That is, almost surely misses them. Yeah, if the Brownian motion starts at a point that's not on the set, then it almost surely misses the set. Polar sets are removable singularities for bounded harmonic functions. That's also a very nice property of polar sets. Now, I want to define a cave domain in Rn, and there's a sketch down below, and I'm sorry I'm not good at making sketches on the computer. A cave domain is a domain which is between the graph of two functions defined on Rn minus 1. These two functions, I call them phi minus and phi plus. Phi minus here and phi plus. And the cave domain U is above the graph of phi minus and below the graph of phi plus. That's how U is defined. So these should be defined. They should be surfaces, hypersurfaces. Now, here's a theorem. So suppose U is I'm sorry. Oh, I should have corrected this graph. Replace phi minus by and replace phi plus by D. So this below here it's the graph of C, and above it's the graph of D. So let U be a cave domain, and choose F prime. A subset of U prime. U prime is, if you look up here at the definition of a cave domain, the domain is parametrized by a subdomain U prime in Rn minus 1. So it's between these two graphs of functions defined on, both of which are defined on U prime. So if we have such a cave domain and F prime is in the parameter space and it's an F sigma polar set, then for continuous function on the cave domain, there's a harmonic function on the cave domain, which has these vertical limits equal to the boundary function. So as take a point in the domain here, and you fix the parameter x prime, and you let y just to the graph below, then it tends to the given. It approaches the given function phi, which the given function phi. I've made another mistake here. It's for every phi. Yes, it's continuous on U. So these both functions are defined on all of you, and one is continuous, one is harmonic, and they have the same limit as you approach vertically, either boundary on top or on the bottom. You have the same limits for a parameter set of points U prime, which is a segment. So as an example, we can as an example we can consider the upper half space. You take a countable dense subset of Rn minus 1, which is polar, and take U to be the upper half space, Rn minus 1 cross R plus. Then if you take a polar subset of Rn minus 1 and define a function over it, then and you call that U, then any continuous function, the graph underneath that surface can be approximated vertically, vertical limits as you approach the base Rn minus 1 on this polar set for all sets in this, all points in this polar set. Now here's an analogous theorem. Instead of a region between two graphs, two surfaces, it's a star-like domain, U and Rn, in polar coordinates. So now we consider Rn as the product of the sphere and real numbers going from 0 to plus infinity. So the sphere is the parameter space, and we choose prime on the sphere, and we choose a function depending on the parameter, the value of theta in the sphere, and we choose two such functions, and then we get a shell domain. If we have just one function, then we have a star-like domain with the outer boundary R of theta. But if you have a shell domain, well, you have an outer boundary R of theta and an inner boundary little r of theta. And then we have a similar theorem here, that if U is a star-like domain in Rn, or a shell domain, and F prime is in the sphere, and it's a polar set, then for every continuous function on this shell, there's a harmonic function on the shell domain, which has radial limits on this parameter set, the same as the initial continuous function as you approach either the inner surface or the outer surface. You can prescribe the limits along the rays. Here's a very nice theorem in complex analysis proved by Lichto in 1955. He showed that if you have two arbitrary measurable functions on the unit circle, then there exists a holomorphic function in the unit disk having psi1 plus I psi2 as radial limits for almost every point of the unit circle. Well, the main result with Shirazi is that we have extended this to several complex variables. if you have two real valued functions on the torus, which is the boundary of the polydisk, you have measurable functions, then there exists a holomorphic function in the polydisk having these given radial limits for almost every point of the torus. So you can prescribe radial limits of a holomorphic functions at almost every point of the torus, of the distinguished boundary. This does not follow from potential theory. Potential theory might give us two harmonic functions, u and v, but we would need for these two functions to satisfy the system of Cauchy-Riemann equations in order to get a holomorphic solution. So this requires a separate proof. Approximating continuous functions. For a compact set K and Rn, denote by P of K the functions on K which are uniform limits of polynomials. The most famous approximation theorem, I think, is that of Weierstrass in 1885. If I is a closed unit interval, then P of I equals C of I. Every continuous function on a closed unit interval can be approximated uniformly by polynomials. This wonderful generalization, the Stone-Weierstrass theorem, that a subalgebra of the continuous functions on a compact set, on a compact space, is dense in the continuous functions if it contains constants and separates points. And as a corollary, if you have an arbitrary compact set in Rn, then any continuous function can be uniformly approximated by polynomials. What about complex approximation? For a compact set in Cn, denote again by abusive notation C of K the continuous complex functions on K, and by P of K the functions on K which are uniform limits of complex polynomials. Well, there's a complex version of the Stone-Weierstrass theorem that a subalgebra of the continuous functions is dense in the continuous functions if it contains constants and separate points, as the real Stone-Weierstrass theorem. But also, we have this additional condition that conjugates. Now, I claim this is not a theorem on complex analysis, but merely a theorem on complex algebra or complex topology, because the conjugate of a complex analytic function is rarely a complex analytic function. For example, the conjugate of the function z goes to z is the function z goes to z bar. It is not a complex analytic function. And so the complex Stone-Weierstrass theorem is not very useful in complex analysis. Now, this is what I consider authentic complex approximation theorems. A very, very powerful theorem was proved by Walsh in 1906. If J is an arbitrary Jordan arc in the complex plane, then the polynomials are dense in the continuous functions. This is quite a deep, very beautiful and deep. Lavrentiev generalized this in 1936. If K is a compact set in the plane with empty interior, then the polynomials are dense in the continuous functions if and only if the complement of K is connected. If and only if K has no holes. Now, let's go from compact sets to subsets of C. I mean, unbounded closed subsets of C. So it's not natural to approximate by polynomials there, because the functions may be bounded and the polynomials not, etc. It is natural to approximate by entire functions rather than. Let's define a closed subset of C to be a Cauchy-Riemann set if for arbitrary continuous functions phi and epsilon on greater than 0 on F, there exists an entire function F such that F minus phi is an absolute value less than epsilon of Z for every Z in F. Well, in 1927, I already stated the theorem of Cauchy, which says that R is a Cauchy-Riemann set. Every continuous function on the real line can be approximated by entire functions. Arakelian extended this theorem in 1964. if you have a closed set of empty interior, then it's a Catalan set if and only if the Riemann sphere minus F is connected and locally connected. That's necessary and sufficient, 1964. I repeat the theorem. Aracelian's original formulation was maybe easier for many people to grasp. Catalan set if and only if for each circle of radius r, there exists a larger circle of radius r prime, such that at any point outside of it, and also outside of the larger circle, can be connected to infinity by a path which still lies outside of F and never returns to the smaller circle. That's a lot easier for some people to understand. I mean, you don't need to know topology really to understand that. The formulation above in terms of connected and locally connected, I think I'm probably the one who found this topological visualization. There's nothing to it. I mean, it's just the theorem is Aracelian's, but I just noticed that it can be written in that way as connected and locally connected. Here's an example. Take F to be the curve z equal x plus iy, where y is equal to sine 1 over x. So it oscillates bigger and bigger and bigger as x approaches 0. And to make sure it's closed, just add the imaginary axis. Then the complement of F is connected. For any point in the complement, you can draw a vertical line going to infinity that misses the graph. But it's not locally connected. These big loops prevent it from being locally connected at infinity. Now here's a generalization, replacing the complex plane with an open subset omega. Take a closed subset, and it's a Catalan set in omega. That is, we approximate by functions holomorphic in omega. If for every, this is a definition now, if for every phi and epsilon in CF with epsilon positive, there exists a function holomorphic in all of omega, approximates phi within epsilon, everywhere on the set F. So Aracelian extended a couple of years later his theorem on approximation by entire functions to approximation by functions holomorphic in omega. Using the topological characterization which I gave, it's a lot easier to state. It's stated exactly the same way. If and only if omega star minus and locally connected, where omega star is the one-point compactification of omega. I repeat the theorem, and here is an example. Take omega to be a rectangle and F a union of horizontal lines. Then omega star minus F is connected and locally connected. I've indicated that the ideal point at infinity is the upper boundary of the rectangle and the lower boundary of the rectangle, but it's also the left boundary and the right boundary of the rectangle. And so since the left boundary is infinity, any point which is not on one of these lines to infinity by a horizontal line in the complement. And so this is an example. I repeat the theorem. And another example, we take a disk of finite or infinite radius and F a union of rays. Then omega star minus F is connected and locally connected. I repeat the theorem again. For arbitrary domains, no, I repeated for the entire case, and then Boivin, in his thesis, extended the theorem to arbitrary open Riemann surfaces. So given a closed set on an open Riemann surface, we want to approximate functions continuous on it by function holomorphic on the whole Riemann surface. Okay, I remind you of the Walsh theorem. If you have a Jordan arc, you can approximate by polynomials. That is not true in CN. Approximation in CN is very difficult and very underdeveloped. Very little is known. But here's a positive result proved with Chacron and Nersessian in 1998. If this domain in CN is a product of domains in, or more generally, if it's a product of domains in Riemann surfaces, if omega J are open Riemann surfaces, then omega is a complex manifold, the product of these Riemann surfaces. And if you have J, which are Caudelemont sets in each Riemann surface, then the product of these closed sets is again a Caudelemont set in the product manifold of these Riemann surfaces. Well, we're interested in the simple case where omega J is the unit disk. And so the product manifold omega is just the polydisk. And here's the result. If we have a continuous function on the polydisk, there's a function holomorphic in the polydisk, which the continuous function along rays tending to almost every point of the torus. So that generalizes the result of the union known for the unit disk. For a proof for the unit disk, I wasn't able to circle. So pretend that the disk is this rectangle, the sheet of paper, and that the left edge is the unit circle, and that the horizontal lines here are rays. Then if we have a parameter set f prime on the unit circle, it's closed and nowhere dense, and it's not nowhere dense. No, it's a countable union of closed nowhere dense sets. Then we can approximate, and in particular, we can get such that the union has measure 2 pi, and so we set f the union of all these rays. I'm sorry, yeah, these are rays because this is the unit disk. The union of all these rays ending at this this boundary set f prime on the unit circle. So each of these each fj is a closed nowhere dense set of rays, each of which is of length 1 over r sub. This should be r sub j, and so these rays get closer and closer to the unit circle. The collection of these rays is a locally finite family. So the union of f is a closed nowhere dense set. D star minus f is connected and locally connected. So it's a Caudelemont set. We can approximate a continuous functions on f by functions holomorphic on D. And I repeat this theorem of approximation on products, and I repeat the particular case for the unit disk. So for the polydisk, the proof is that we showed how to do it for n equals 1, and then we used the theorem on product, the CGN theorem, to get it for the polydisk. Okay, I repeat the theorem that we just proved here. And as a consequence of that, we get that if we have arbitrary measurable functions on the polydisk, on the torus, then they're just a holomorphic function on the polydisk, having these radial boundary values at almost every point of the torus. Theorem that I stated much earlier, but now we have an idea of how to prove it. It follows from theorem 1 that says you can approximate a continuous function, provided you have this lemma that given the boundary data, that there exists a continuous function having these radial limits at almost every point. This may seem contradictory, but we are not asking that the continuous function have a continuous extension to even one single point of the torus. It's continuous on the polydisk, and we don't say that it extends continuously, just that it has these boundary limits on each ray. Its restriction to rays are continuous, certain rays. I repeat the lemma. Now, I've stated it as continuous functions instead of from, we're interested in the case where these functions take their value in the extended real line, minus infinity to plus infinity. But we're not used to thinking of CT extension for functions which take the value infinity. And so that's why I stated for minus C to plus C. But the theorem is topologically equivalent, no matter whether C is infinite or minus or finite. It's topologically equivalent. So it's enough to prove it one. And there we're comfortable with Runge's theorem, and we're comfortable with the CT extension theorem. So here's what we do. We have these subsets of the torus, which are compact and nowhere dense. And by Runge's theorem, so we have these such that the restriction of psi to each of these sets is continuous. Careful, it's not psi that's continuous. Runge's theorem says the restriction is continuous. And then we consider the union of these. And we can take them such that the Haar measure of the one. Because you can, in measure, you can approximate compact sets by subsets of which are completely, which are nowhere dense, with Cantor type sets. So given these subsets on the boundary, then we take these, just extends them into the inside by these rays. But notice that these rays get shorter and shorter. And then we extend the restriction on the boundary sets to continuous functions on the rays. And then we have the limit of this extension is equal to the function by definition. Now this extension is only defined on these rays, but all these closed subsets of the polydisk form a locally finite family of closed sets. And so their union is also closed, and their function phi, which was continuous on each fj, is also continuous on the union because the family is locally finite. So now we have a function continuous on this closed subset of the polydisk, and we extend it continuously to the whole polydisk. Notice an important point here is that we used a refined CT extension theorem that says that even though our boundary function may take the value plus and minus C, the extension, we can take the extended function, which takes its values omitting minus C and plus C. So that's how we, even though boundary values, we get finite valued holomorphic functions when we're all finished. So we have just proved this lemma. And as we said, this lemma gives us this theorem, which we already stated, about existence of holomorphic functions with boundary values. First of all, that approximates a continuous function, and therefore we can get with the given boundary values. How am I doing for time? I don't have a clock in front of me.
You have about 10 more minutes, Paul.
Okay, thank you.
Yeah.
I think maybe I'll finish before. The set of boundary values at which a continuous function has radial limits is measurable, and the radial limit function is measurable on this measurable set. We have the following converse. Take any two measurable subsets of the torus. and take any functions defined on these measurable sets. We allow the values plus and minus infinity. Then there exists a holomorphic function in the polydisk, therefore finite valued, such that the real part tends to psi1 for almost every point of A1. The imaginary part tends to psi2 for almost every point A2. And the cluster set elsewhere is total. Cluster set of U on the complement of A1 is total, and the cluster set on the complement of A2 of V is total. For CR, U theta is the radial cluster set of U at theta, similarly for V. So I remind you of the definition of the radial cluster set of a function U defined in the polydisk at a boundary point theta. It's the set of all conceivable values, finite or infinite, which can be approached by U along a sequence of points on this radius ending at theta. It's the set of all values that can be approached by the function along the radius ending at theta. That's the radial cluster set of the function U at the boundary theta. So we have these prescribed measurable boundary values on prescribed measurable sets, and outside of these prescribed measurable sets, all values are approached. All values are approached. What we have shown, for harmonic functions, you can prescribe limits along segments ending at a subset of the boundary, which is small in the sense of potential theory, a countable union of closed polar sets. For holomorphic functions on the polydisk, we can prescribe limits along radii ending at a subset of the boundary, which is topologically small, a countable union of closed sets. An important difference is the sets which are topologically small can have full measure, while polar sets are of measure 0. So we have shown this theorem in the polydisk. There's a similar theorem recently published in 2020, Gans and Min, for holomorphic functions on the ball in CN. So it's quite similar to our results. Very same sort of statement for behavior approximating continuous functions on radii at almost every point of the boundary. And that extends earlier work by Hakim and Sibani. We have not been able to find how our result on polydisks could follow by their result on the ball. Their result is not only for the ball, it's for certain star-like domains, but still we couldn't see how they have additional hypotheses, and we couldn't see how to adapt those for proving our result in the polydisk. Merci.
Thank you very much, Paul. Let's thank the speaker first. Any question or comments for Paul? Indeed, I have several. I don't ask them all. Maybe later on we discuss Paul. The Carleman theorem that you mentioned, I haven't seen the proof. Is it kind of elementary or it has many details?
Carleman's proof was rather technical. It involved approximating using Runge's theorem, approximating on a disk, and then approximating on what I call Saturn. You add a little segment on each side of the disk, and then you take a larger disk containing matter, and you approximate by a polynomial, and then you add 2 more segments. So you keep adding more and more segments going to left and right, tending towards the real line, and you're exhausting the plane with these larger and larger disks. And the technical difficulty was approximating simultaneously on the disk plus these two segments that you join at the 2 points, because you had to you didn't have Mendeleev's theorem available, and so you had the function which was holomorphic on the disk, but it's only continuous on these segments on the left and right side of the disk, and Runge's theorem doesn't cover that, and so it was quite technical for Carleman to show that, but Carleman's theorem has been extended to several complex variables, like Scheinberg, and he uses an integral representation for functions on Rn, and it's in that sense it's neater than Carleman's theorem, and the amusing thing is. I'm sorry. The amusing thing is that this integral formula, Carleman's theorem in several variables, is actually the proof of the original Weierstrass theorem. In all the many books on approximation theory, there are many proofs of the Weierstrass theorem. The original proof is rarely given. The original of Weierstrass, to approximate a continuous function by polynomials on an interval, he approximated by entire functions.
Oh.
He took the power series and got polynomials. To approximate by entire functions, I don't know whether Scheinberg knows this, but he used the same integral representation that Scheinberg used in several complex variables. Weierstrass used that.
Okay. Thank you, Paul. There is a question in the chat asking, is compactness a necessary condition in Weierstrass theorem?
It's natural, of course. If you want to approximate uniformly by continuous functions, it's natural to assume that the set on which you are approximating is closed. Because if you have a sequence of continuous functions that converges uniformly it converges uniformly to the closure. And so the original function will extend continuously to the closure. So closedness is certainly natural. As for compactness, it is also natural to, if you want to approximate by polynomials, if the set is closed and not compact, the only continuous functions you can approximate are the ones that go to infinity. You can't approximate bounded functions except constants. Polynomials unbounded set are unbounded, and so you're too limited.
Okay.
Nevertheless, there's a school of approximation theory which has approximated functions on the real line by polynomials, but it's a weighted approximation. It's not, it's weighted.
Another question is, why extending to several variables so difficult? I don't know what he or she means so difficult. I mean,
well, I was hoping to suggest that when I said that even on a Jordan arc, you can't always approximate continuous functions, polynomials in C2, but there's a very natural condition that helps to approximate in several variables, and that the condition of polynomial convexity. If you assume a compact set is polynomially convex, then you have a Runge theorem. Every function holomorphic in a neighborhood of a compact set can be approximated uniformly by polynomials.
Mm.
We approximated in C on compact sets. Mendeleev's theorem gives you completely topological characterization, and in several variables you have topologically equivalent sets, and for which you can approximate on one but not on the other.
Thank you. Any further questions or comments for Paul? If not, let's thank him again. Thank you.